recording. Okay, so again, up to you. If you want to stay with your video on, that'd be great for me. If you're not comfortable doing that, I understand. And if you can stop your video if you want. The only thing I would ask is if you are going to, talk to everybody, just briefly unmute yourself, okay? But you don't have to leave it on the whole time if you don't want. I get it. Okay. So what we're going to be doing today is we're going to be talking about limits and continuity. Okay, I kind of mentioned this in our last class, and I said that was the key to understanding instantaneous rate of change. Exactly how fast is a function changing at a particular input or x value. Okay, so that's where we're going to go today. This is the first real calculus topic. Okay, so yay, we're doing calculus today. I'm going to start out by sharing my browser with you. Let's see that I can actually do that. Okay, here is everybody should be able to see, yes, my WebEx thing. And I want to go into our course. All right, so everybody should be able to see our course. And we are currently in week 2. Okay, and again, we're going to complete all of this by September 5th, which is Sunday. We did instantaneous rates of change and tangent lines in class on Monday. And today we're going to be talking about limits and continuity. Okay, so sections 2.1 and 2.2. I am going to be using the limits and continuity notes today. Okay, average and instantaneous rate of change are the notes I handed out in class, or that you printed off. Thank you. Okay, but for these, okay, pretty much if you want to do any writing while we're going through class, you're going to need to have a way to print these off. I spoke to some of you after class on Monday, and you're more than welcome to use the printers in the LRC. Okay, so when you're in there, when you come out of LRC 102, if you want to just follow me around the corner, I can show you. You can get on any of the computers in the LRC and print to the large printer by the front door. Okay, and that way you have your notes for Wednesday's class. Okay, so I'm going to be sharing these with you right now. Okay, so give me a minute to do that. Okay, and let me share that content with you. Okay, so everybody should be seeing limits and continuity notes. Okay, I'm going to open the chat, so pretty much if you've got a problem, either unmute yourself right away and say, hey, I'm not seeing it, or just type in the chat. Okay, everybody got this? Okay, can somebody just unmute and say, yeah, I can see it?
Yes, ma'am, you're good.
Yeah, we can see it.
You're good. Okay, thank you. Got to make sure everything is working before we just launch on. Okay, so like I said, again, I'll be uploading these notes along with the video. Okay, so you'll see all of my answers to the questions in here. Now, the idea of a limit is different from the idea of a function value at a particular x. Okay, if you remember when we're talking about instantaneous rates of change, we're talking about what's happening as we get closer and closer to an x value, right? But we're not actually at the x value. Okay, that highlights the difference between a limit and a function value. Limits describe the behavior of the function when your independent variable is near but does not equal a given number. Okay, so it's the behavior near an x value. Okay, how near? Well, as near as you want to be. Okay, as near as you want to be. Okay, so as you get closer and closer to, say, the x value, you're paying attention to what's happening to your f of x values, okay? If they get closer and closer to a given number, okay, you would say that that number, your f of x values, your y values are getting close to, is the limit as x approaches a given number, okay? So here's the terminology, the way we're writing it. Okay, so if the values of f of x get closer and closer to some number L, as we make x get closer and closer to another number C, we say the limit of f of x as x approaches C is L. Okay, don't worry, it'll get clearer. And I even have a little activity in Desmos that you can play with to get the hang of this. All right, so in some cases, okay, the function value at C will be equal to the limit at C. But in lots of other cases, it won't. What other cases? Well, when there's a hole at C, okay, or where there's a jump at C. Okay, so let's take a look, okay, at this graph here. Okay, and I'll go through some examples. By the way, this little arrow under the limit statement means approaches or gets close to. Usually people read it as approaches. So again, the way this is read is the limit, that's lim, as x approaches C of f of x is L. Okay, and again, the limit, the value of the limit is a y value. It's an output value. Okay, whereas this value down here is an x value. All right, so let's take a look at some examples. Okay, let's take a look at this graph down here. Now, again, I have a nice curve here, and you can see as I travel along the curve towards x equals 1, I'm getting closer and closer to the y value 2. The same thing is true if I approach x equals 1 from the other side of 1, coming down the curve. You can see I'm approaching the y value, the f of x value of 2. Okay, and you're probably looking at it saying, yeah, well, duh, when you actually get to x equals 1, the function value is 2. Yes, okay, that's a nice, smooth, well-behaved function. Okay, so what I'm going to write over here is I'm going to say the limit as x approaches 1 of f of x is 2. Okay, and I could say also f of 1 equals 2. Okay, does everybody understand what I wrote here? Okay, I'm saying when I'm near x equals 1, I'm getting closer to f of x equaling 2. And when I am right at 1 here, I'm equal to 2. Okay, so does that make sense? Make sense?
Yeah.
Okay. From time to time, I'll type stuff in the chat or I'll ask you. Again, feel free to unmute and comment. Type in the chat if you're more comfortable doing that. I got the chat open.
I had
All
a
right,
question.
so that,
Can you repeat what you said again?
okay, which part?
Where you said when it
Jennifer?
approaches a 2?
Okay, imagine you're riding along this blue graph, right? I'm riding along the blue graph. I'm getting closer and closer to x equals 1 down here. See, if I could come from the left, what y value am I getting close to? Well, I'm getting close to the y value 2. See? Likewise, if I come at it from the other direction, okay, if I approach x equals 1 from the right-hand side, I'm also getting closer to y equals 2. That's the idea of the limit. Okay, when I get near x equals 1, I'm getting nearer to y equals 2. And it just so happens that this particular x value, okay, when you're right at x equals 1, y is exactly 2. That's what I wrote here with function notation. This part that says also f of 1 equals 2. Okay, so the limit as x gets close to 1 is 2, and also f of 1 is 2. Okay, because the function is nice and smooth and well behaved here. There's no weirdness at x equals 1. Okay, is
Thank
that
you.
all right?
Yeah,
Okay,
that sounds good. Thank you.
and again, feel free to keep asking if it's not clear, okay? All right, let's look at weirder stuff, okay? Take a look at x equals 2. Okay, everybody see the open circle there at x equals 2?
Yeah.
Okay, what that means is f of 2 does not exist, okay? Or you can use the word undefined, okay? There's no output value for x of f of 2, all right? When you're right at 2, there's nothing. There's a hole, okay, in your graph. You probably remember these from working with rational functions in Math 151. Okay, so everybody see that? Now, that doesn't mean the limit doesn't exist, because if I, again, keep traveling on this graph towards x equals 2, what y value am I getting close to? 3. Same thing as if I approach x equals 2 from the left-hand side. I'm getting close to y equals 3. Okay, so the limit as x approaches 2 is 3. But the function value at 2 does not exist. Okay, so I'm trying to highlight the difference here between the limit and the function value. Okay, so here's a hole. Okay, and you can see these don't match. All right, first case they matched because, again, nice smooth function here. Questions so far?
So anytime that there's a hole in the function, it's just it does not exist.
Well, the output value does not exist. That's what a hole means, right? That's what this open circle means. It means there's no y value there.
Oh, I see. Okay.
Okay. Another situation, okay, is if your function shoots off to infinity, right? At a vertical asymptote, say you have a vertical asymptote at x equals 0, the y-axis, and your function shoots off to infinity there. You're never going to equal x equals 0, right? Because as you keep getting closer and closer and closer to it, the function keeps shooting up. Okay? So again, most of the weird behavior happens in rational functions or in piecewise defined functions. If you've got well-behaved functions like polynomials, not so much. Okay, the limits and the function values are going to be the same there. Okay, but if you've got functions with holes or jumps, that's where you're going to have a difference between the limit value and the function value. That's part of the reason why you studied a whole lot about function behavior in Math 151 before getting to a calculus class. Okay. All right, let's take a look at x equals 3. We're over here. Again, you see an open hole, okay, in the smooth part of the function value, but you know what? The function is defined at 3. Anybody tell me what is the value of f of 3?
1.
Okay, well,
I'm gonna
that's where
say 2 because
that's
there's
where the
that.
hole
Oh.
is. Yeah, where's the solid circle? The solid circle is up at 2. Okay, so this is kind of like a function. This would be a piecewise defined function that says, in general, your function output value is the smooth curve, but when you get to 3, it's this value instead. Okay, kind of like an exception value. Okay, so f of 3 would be 2, but as you're thinking, right, if I ride the curve towards x equals 3, I'm getting closer to y equals 1, like you thought, right, where the open circle is. If I ride the function as I come over here, okay, from the right side towards x equals 3, I'm also getting closer to y equals 1. So that is the limit value. But you can see the function value at 3 is a different number. Okay, so here's another case where you have a hole, but you do actually have a defined value of the function. It's just somewhere else. Okay. Is this okay?
Yeah, that makes sense.
Okay. Everybody getting the hang of this? Okay, limits are what happens near the value. Okay, and otherwise it's the actual function value. Now let's take a look at 4. Okay, 4 is a special case. I think you can all tell me what's the function value at 4. Where's the solid circle?
It's at 1.
Yeah, so right at x equals 4, you see the graph's up here doing stuff. There's a jump in it, and the actual function value is at 1. Okay, so f of 4 is 1. Now let's take a look at limits. Imagine again, I'm writing this function, and I'm coming up towards x equals 4. Here, on the left side, I'm approaching one y value. Okay, so here I'm getting close to y equals 2. From that side, everybody understand? From the left, I'm getting close to y equals 2. But here's the other arm of the function. And if you approach x equals 4 from this side, what y value are you getting close to right here?
3.
Yeah. Okay, so you can see you're getting close to 2 different values. Can you decide which one to pick for the limit?
No.
Are you not
No.
You
going
have to
to
put
right?
both.
I'm sorry, say again.
You're not going left to right here?
You're basically, again, we're making a point here is in order for you to have a limit value, the value that you're approaching has to be the same from both the left and the right.
Oh.
Okay, so if you've got a jump like this, you don't have a limit. All right, so again, you're thinking as that the limit from the left is 2, the limit from the right is 3, so we say the limit does not exist. Okay, why does not exist? Because you can't tell which one to pick. All right, and there is actually some notation that would tell you you're approaching it from the left or the right. Okay, so the way I would actually write this, I'd say the limit as x approaches 4 from the negative side, right? That's the left side, all right? Left of 4, I'd write it like this, okay? Of f of x equals 2. And then you'd say the limit as x approaches 4 from the right side, which is the positive side of the x-axis, of f of x equals 3. Okay, so this is from the left from the right. Okay, and as soon as you see 2 different values for the limit from the left and the right, you know the limit itself as x approaches 4 does not exist. Okay, so I think these are kind of all the varieties of what can happen with limits graphically. Okay, I wanted to make sure to show you the terminology a bit first. Make no mistake, you're learning a foreign language. Okay, and if it seems like, wait, I'm kind of swimming in this, it's like because you're learning some new vocabulary and terminology. Okay, so let me stop and ask if there are any questions at this point. Questions so far? Anybody? It'll get better, I think. Okay. As a matter of, go ahead.
So it asks for us to determine the following limits. So the answers would be the f or the y values, or the answers would be those numbers on the left.
Okay. Basically, if you're looking at example 1 right here, The
Mhm.
answers are the y values. So 2, 3, 1, and does not exist.
Okay, so you
But
don't
a
have to
limit,
sum
yeah,
those
limit
parts.
value is an f of x value. Yes.
Okay, cool.
The x value is down here under the lim thing. That's telling you what x are you trying to get close to. And this is the y value you're trying to get close to as you do that. Okay. Now I understand this is a whole lot of words with a static diagram. So what I have that I want to share with you, okay, I'm going to try to stop sharing and come, I think I have to stop sharing. No, I don't think I have to stop sharing. Let me see if this works. Okay, I'm going to put a link in the chat. Okay, it's for a Desmos activity. The majority of you signed into Desmos last time we were on together. Okay, and this is like a limit activity that you can play with. Okay, so I'm going to see if I can back out of this one. Okay, meanwhile, what I need you to do is copy that link and try to open it in another tab. Okay, on your computer or your tablet. Okay, try to open that in another tab and get into it. And I am going to see if I can get into it here. Righty. Cover the chat. All right. Distance limits and continuity. And I'd be able to watch you guys get in. I also going to anonymize you. Okay, so by anonymizing you, what I've done is you don't have to worry about your privacy. You've all been renamed as a famous mathematician. Okay, so you've got Elbert Cox, you've got Grace Adele Williams, okay, Alan Turing. These are all famous mathematicians. Okay, access to social features. Okay. And then I should be able to see you as you walk through the activity. Okay, so the activity again is simply showing you a function with limits. Okay, there's only 4 slides in it. So try to, take a look at it. Okay, and work through the slides. Okay, and I'll be looking at what you're doing on another computer. Okay. Okay, is everybody able to get into this activity? Okay, because I'm missing 2 of you. But yeah, okay, everybody's gotten in. So we are probably down on 2 people. I know one person is
But
out. So yeah,
I was doing it and I got to like the 4th question and then like everything disappeared.
it disappeared. Okay, it's only basically a 4-question activity. So you'll be able to backspace over the 4 slides.
Okay, yeah, I got to the 4th one, but
Yeah.
I don't know what happened.
Okay, so it's gone. You can't get back to it.
Yeah, like this, or I could get back to it probably.
Yeah,
just
get back
fell
to
off
it.
the
Yeah.
tab.
And I just basically need to see how you're doing on it.
All right, I'm back in it again.
Okay. Okay, so hopefully this example is helping people see with like something that's animated. Okay, what happens when you've got a break in your function? Okay, so you could see when you approach the value from the left, right, as x approaches 1 from the left-hand side, and on that last slide, okay, you can see the notation x approaches 1 with a little negative sign.
Is there
Okay,
any
that's
way you could put the Desmos on your screen just so we could see what you're talking about at the same time? Or should we just?
okay. Yeah.
Actually, that was a dumb question. I'll just go look at mine.
Okay, I'm in here as a student. Okay, can everybody see this? Okay, it says watch the dot as it moves along the function y equals f of x.
Yeah, I can see it.
You can see it? Okay. And you can see
Okay.
as it's moving close to x equals 1, it's getting closer to y equals 2. Now notice there's an open circle in the graph there. So it doesn't actually ever equal y equals 2 here, okay? But I can say as the dot is getting closer to x equals 1 from the left, okay, this is approaching 2. Okay, y equals 2. Everybody see that?
Yeah.
Okay. Then I'm going to go to the next slide, and you can see it's approaching x equals 1, but this time from the left side, the right side rather, and it's going all the way up, and you can see it's getting closer to y equals 3, but there's an open circle there, so it's never going to equal it. All right, so I'd say it's getting close to the y value 3. Everybody good with that? Okay. Now, if you actually look for where the dot is in this graph, you can see the function value at x equals 1 is somewhere down here around 1/2. Okay. So again, like I'm saying, when you're thinking of limits, imagine taking a ride on the graph exactly like this little dot. Okay. And ask yourself, what y value am I getting close to? And you have to look as you approach your x value both from the left and from the right. Okay. In this case, okay, I'm not getting to the same y value. You can see I got 2 when I'm approaching from the left, and I got 3 when I'm approaching from the right. Okay, the actual function value, I guess 0.5. Okay, it looks like it's midway between 0 and 1. Okay, and the last slide, okay, says select an option to see how mathematicians would describe what you saw on the previous 3 screens. Well, basically, the limit as you approach 1 from the negative side, the left, is 2. Yeah, that's right. Okay, the limit as you approach 1 from the positive side, the right, is 3. Yeah, and the actual value of the function is 0.5. Okay, so what happens if I choose these? They actually read it to me. Okay, the limit of f of x as x approaches 1 from the left, that's the little negative sign up here, is 2. Okay, here, the limit of f of x as x approaches 1 from the right, that's the little plus sign, is 3. And the value, the function value at 1 is 0.5. Okay, I know it says move on to the next screen, but I kind of excluded that. I just wanted to try a little bit just to see how it works. Okay, so did this work for you? Did this activity help?
I liked it,
Yeah.
honestly.
Yeah, I liked it.
Okay. I'm going to try to get a little bit more fluent with Desmos Teacher and try to put some more of these activities in the course that actually give you a chance to play. Believe it or not, calculus, since it's the math of things in motion, really lends itself to apps like this. Okay, so when you see things moving, then what we're trying to do actually makes a little more sense. Okay, so all right, well, great. Thank you all for trying that. And again, any questions on the activity before we leave it? Any questions? We're all good?
No, I'm all good.
Okay. All righty. Well, I'm going to go back to my notes if I can find my meeting. Where is that? Okay, everybody seeing the notes again? Everybody good with that? Again, I just need to make sure the technology is working like I think it is. All right, so we've got the notes, right? So that's graphical limit finding, but you know from college algebra that there are lots of different ways to render a function, right? To describe a function, you can describe it in words, right? Like the number of ounces of formula you need to feed a baby every so many hours. Okay, so the hours are your independent variable, you know, whatever. So that's description. You could also have a function rule. Okay, and that's probably what you've spent most of your time in algebra doing. By a function rule, I just mean an equation that describes the function. Okay, we've already played with a graph. You know that if I can graph a function rule, I'm going to get a picture like this. Okay, and then you can also probably look at a table of values. Okay, that's probably the most familiar to you if you've used a TI-84. Okay, where you can put the function rule in the y equals window. You can click graph, you can get the picture, and then you can click table, and it'll give you the XY pairs. Okay, so there's a whole bunch of different ways to do this. Well, that means there's different ways to determine limits. Okay, you can do them graphically. Notice here, I didn't have a function rule. They just gave me the picture. Okay, this is some sort of piecewise function. It would probably have a complicated function rule, but the picture is a little bit easier to work with. Okay, but let's take a look at some function rules. Okay, and this is where you kind of have to remember a little bit of college algebra. Okay, let's take a look at this function rule. Okay, and let me ask you a question. Okay, what sort of function is f of x? What sort of function is this? Okay, you can type it in the chat, you can shout it out. Okay, all right, we've got a quadratic in the numerator and a linear in the denominator. Okay, so what kinds of functions have x in the denominator? What kinds of functions have an x in the denominator like this? Okay. Maybe it would help to graph the function for you. Okay, so I'm going to go over to Desmos briefly, the graphing calculator, and I'll graph the function. Okay, so I'm going to put in parentheses y equals, go ahead.
A parabola.
Okay, well, that would be the numerator of it, would be a parabola.
Oh.
Okay, but there's more than just the numerator, right? It's got a denominator too.
So is it going to end up being a linear one?
Take a look. Okay. Okay. Now everybody's looking at it saying, hey, it looks like a straight line. Okay. This isn't a linear function and it's not a quadratic function. Okay. You might remember it as being a rational function. Okay. Rational comes from the word ratio. Okay. Which means 1 in the numerator divided by 1 in the denominator. Rational functions are the weird ones that tend to have asymptotes and holes. Okay. Now you might remember, okay, that what determines whether you've got holes or asymptotes? Well, asymptotes are really visible on a graph. Okay, but when you have holes, some weird things happen. Okay, so let me go back to the notes. Okay, and I'm going to just put a note over here saying rational function. Okay, even though it graphs as a straight line, it's not a linear function. Believe me, it's not. Okay, and I'll show you why in a minute. Okay, if we were to factor the quadratic in the numerator, okay, you can see what would happen. Okay, and again, I'm not going to waste any time on this. Anybody notice anything? Okay, I promise I factored the quadratic correctly. Anybody notice anything about the resulting factored expression?
I mean, you could cancel out the x minus 1.
Well, basically, what you want to notice is you have the same factor in the numerator and the denominator. And if you remember from college algebra, okay, we are going to do some canceling eventually to find the limit, okay? But the same factor means there's a hole when x minus 1 equals 0, or at x equals 1. Okay? So essentially, what this is telling you, the matching factor in the numerator and denominator, is this function has a hole in it. Okay? This function has a hole in it. And again, if I go, again, forgive me, I'm going to go back to Desmos briefly. The hole would be at x equals 1, which unfortunately they're not showing on the graph, but if I zoom in, maybe they will. Yeah, here we go. So here's x equals 1. If I go up here, what do you see as the y value?
It says undefined.
It says undefined, yeah, and it's hard for me to hover on it and get exactly there. I'm sorry. There you go. Okay, and you can see if you look under my cursor, it is an open circle. Okay, so that's the hole in your rational function. This rational function doesn't have asymptotes, it just has a hole. Okay, which means it graphs, so it looks linear, but it's not linear because linear functions don't have holes in them. Okay, so that's kind of important to realize. Okay, now let's take a look at some other stuff. Okay, so one thing I can do, I'm all over the place here. Okay, so one thing you can do is, it says you can't really evaluate the expression when x is 1 because the function output isn't defined there. Okay, so you can't say, well, I'll just plug a 1 in. You're going to get 0 divided by 0, and that's an undefined thing. Okay, but what you can do is you can make a table. Okay, so here's a table, for example, like a TI would have. Okay, and I can get close to x equals 1. First, I can be at 0.9, then 0.9998, then 0.9994. You can see I'm putting in values that are getting closer to x equals 1 from the left. Okay, and you can see what's happening to the y values. What's happening to f of x as I get close to x equals 1? These values are getting close to what?
Keeps getting smaller and smaller to the decimal, I guess you could say.
Okay, but what are these f of x values getting closer to?
Oh,
3.
3.
3.
Sorry.
Right? No worries. Closer to 3. But you can see they're getting closer to 3 from the low side, right? When we're right at x equals 1, we're right at the hole. Okay, so my output value is undefined. Okay, then if I am getting closer from the left, from the right, now take a look, you got to read the table backwards. Start at 1.1. That's a little bit past 1. Then go down to 1.003, 1.00001, 1 and 5 zeros and a 7. This is really close to 1, but from the right side. Okay, so 1.1 is farther away from 1 than this, 1.000007. That's really close to 1, but it's only slightly to the right. And you can see, reading this part of the table backwards, the function values are also getting closer to 3. Right? So this is getting closer to 3 this way, getting closer to 3 the other way. Everybody kind of see what I'm showing you here? Yeah? Everybody understand the table?
Yeah, that makes sense.
Okay.
Yeah.
So what you're seeing in tabular form is the limit exists. The limit as x approaches 1 is 3. Why is that? Well, as I get close to 1 from the left, y is getting closer to 3. As I get closer to 1 from the right, y is getting closer to 3. So that's the limit. But again, the function value, f of 1, does not exist. Okay, the actual function value is undefined. Okay, makes sense. All right, you can do that on the graph in Desmos as well. Okay, by just simply eyeballing the graph. You got to find the hole first, though. Okay, so you can see here as I ride up the graph this way, I'm getting closer to a value, right? As I get closer to x equals 1 from the left, I'm getting closer and closer to y equals 3. And as I come down the graph, I'm also getting closer to y equals 3. But right here at 3, we're undefined. Okay, but you can see the limit graphically as well. Okay, the important thing is your graphical answer, your table of values answer, and your function rule, your algebra answer need to all match. Okay, you shouldn't get different answers from the different methods of looking at it. Okay, now somebody, I forget who said this, but somebody said, hey, can't we just cancel out the common factor? Okay, well, as long as we're not right at 1, okay, that's what this means down here. As long as x is not 1, it's valid to divide out the common factor. Okay, so when we're near 1, it's okay to do the divide. Okay, and that leaves you with the linear value 2x plus 1 that you're seeing on the graph. Okay, then all you need to do then is plug in 1 to what's left, and lo and behold, you're going to get 2 times 1 is 2 plus 1 is 3. That's the limit. Okay, and here it is, kind of a graphical zooming in of what I had in Desmos. Okay, is everybody okay with this example? Okay with the example? Again, what I'm trying to show you is, again, the algebraic method, because sometimes it's a hassle to graph it. Not always. Okay, that was more of a case in the past. But sometimes you won't have a function rule. Okay, so hopefully everybody is good with this. Okay, if you got questions, ask them. Okay, so again, you're getting the same answer from the algebra. It's telling you the limit is 3. Same answer from the table. Okay, we can see the limit is 3. And again, same answer from the graph. You can see the limit is 3, right? Because we're getting close to y equals 3 as we approach x equals 1. Okay. All righty. So occasionally what I'll do in these notes is I'll excerpt pieces from your online textbook. Okay, that doesn't mean you shouldn't read the text. Okay, because I'm hitting the high points. The text has far more examples and helpful hints. Okay, it's just that, again, I don't want to read the book to you for our lecture. I just want to hit the high points. Okay, so if you look at the table, you know, as you approached the value from the left and then from the right, we got closer and closer to the limit value of 3. Okay, that's not necessarily true in all cases. Like we saw in that first graphical example where we had the jump in the graph. Okay, then the left and the right limits were different. Okay, so here's some definitions about the left and the right limits. Okay, so the left limit as x approaches some number c is L if the output values of the function get close to L as you want, however close you want, when you get close to the left of C. And again, that's when you write this with the little negative sign. Okay, so this is as x, I'm sorry, it's a little blurry. X approaches C from the left. Okay, and here's the right limit. Okay, as you approach the same C, but from the positive side of the x-axis. Okay, so again, the thing to remember is your value, your x value is going to have a negative sign when it's a left-hand limit, and your x value is going to have a little plus sign above it when you're approaching from the right. Okay, and I know you're used to reading graphs from left to right. Okay, and that's generally the case. We are going to do that. It's just in this limit situation, it's important to justify that both the left and the right limits match if you're going to say the limit exists at C. Okay. All right. So let's take a look at some more stuff. Okay. And again, here's the function f of x. I don't have a symbolic rule. But again, let's approach x equals 0. Okay, we're going to say that's right here. Okay, and as I approach x equals 0 from the left, I'm getting closer and closer to y equals 1. So I would say the limit as x approaches 0 from the left of f of x is 1. See? Also, the function value at 0 is 1. Okay, so also. Okay. Now, again, if you're looking at this part of the graph and you're approaching x equals 0 from the left, you're getting closer and closer to y equals 2. Okay, so here's the notation for this part. The limit as x approaches 0 from the right of f of x is 2. Okay, now again, since I've got two different limit values from the left and from the right, then what I'll say is the limit as x approaches 0, notice no plus or minus here, does not exist. Okay, and I believe in your homework, they use the abbreviation DNE for does not exist. Okay, everybody good with that? Okay. Now, if we look at 1, x equals 1, okay, as I approach x equals 1 from the left, my function value is getting close to y equals 1. As I approach x equals 1 from the right, my y value is getting close to y equals 1. Okay, so that limit, okay, the left limit is equal to the right limit, which is equal to 1. Okay, so I can say the limit as x approaches 1 is 1. Now you can see the function value at x equals 1 is -1 because the dot is down here. Okay, so again, the point I'm making is limits and function values are different things. Okay, especially when you've got rational functions, piecewise functions. Okay. Okay, everybody okay so far?
Could
Go
you
ahead.
repeat that last thing one more time? Would you say
Say, which part do you need to hear, Alec?
that very you said about piecewise right before piecewise functions and linear functions? You said that the points are different or something like that.
Okay, what I was talking about was this example. Okay, as x approaches 1 from the left, y is approaching 1. As x approaches 1 from the right, y is approaching 1. So the limit exists at 1. The function value is a different number, right? F of 1 is down here at -1. See the circle? So the limit is 1. The function value is -1. Okay, they're not the same thing. Ask more questions, guys. This is not intuitive. Ask questions.
Did you say that the limit and function values are different?
They are different, absolutely. Right here at x equals 1, okay? Right? If you ride along the function graph, you can see we're getting close to y equals 1, both from the left and from the right. That's the limit. It's down here, right? This says, as I get close to x from the left, the y value equals the same value as I get close to x from the right, and that is the limit 1. See? It's where the hole is. I'm getting closer and closer to y equals 1. The function value at 1 is down here where the solid circle is. So f of 1 is -1. Yes, they are not always the same. More questions. Come on, I know you have them. Ask. No?
Makes sense now.
It makes sense now? Okay. Let me ask you about 3 over here. As x gets close to 3, okay? From the left, what are we getting close to? What y value?
-1.
Yeah. And from the right, as we get close to x equals 3, what y value are we getting close to?
+1.
+1. Are those numbers the same?
No, so it does not exist.
The limit does not exist. Does the function value exist?
Yes.
What is it?
2.
It's 2. See it up here?
Mm-hmm.
Okay. All right. Okay. You can also have situations where neither the limit nor the function value exists, and that's pretty much going to happen at asymptotes. Okay, where a function shoots off to infinity. Okay, if a function shoots off to infinity, you're not getting closer to any particular y value. You're just keeping on, keeping on. Okay, and you also know from college algebra that a function is undefined. The y value doesn't exist at the asymptote. Okay. All right, so that's an example of where neither the function value nor the limit exists. But you know asymptotes are weird things anyway. Let's back up a step. Why do we care about any of this? Well, we're going to be using limits to do calculus. Okay, so it's worth understanding the concept of a limit. Okay, and again, remember, one of the first things we're going to do with calculus is figure out instantaneous rates of change without making tables. Okay, of things. Okay, I don't want to have to make a table to tell me what value am I getting close to and stuff like that. Okay, so we need to understand limits for that. Okay, the other thing we're going to talk about a little bit later today is this concept of continuity. Okay, think of we want to kind of know where potholes are in functions. Okay, like here and here and here, because calculus doesn't work too well there, right? So we kind of need to understand the idea of when is a function not continuous. Okay, and again, there's a definition of what that means, but you can kind of get an intuitive feel for it by looking at this graph. Okay, if I were to draw this function, I would have to pick up my pen to get from here to here. That's a discontinuity. Likewise, if I draw this part of the function, I have to jump over the hole and draw the function value down here. If I have to lift my pen from the paper, that's a discontinuity in the function. Okay, calculus doesn't work well at discontinuous places. All right, so it's a good idea to figure out where that's happening. Okay, so that's kind of why we're spending all this time on limits and continuity. Okay, so let's take a look at some examples. All right, yay, we switched colors. I'm so glad. Okay, so here is a function that looks like it's been run through a lawnmower. Okay, it's some kind of a piecewise function. Okay, it's not a pretty function. It's not like a polynomial or anything. But let's see if we can work on it. Now, basically, what I need you guys to do is to work with me, and then I'll ask you to kind of finish each one of these A, B, C's, and D's, okay? So let's take a look as, again, here's your x-axis. Here are the values on the x-axis, all right? Here's your y or your f of x axis. Okay, everybody should know y and f of x mean the same thing, right? So as I approach x equals 1 from the left, what y value am I getting close to?
2.
And how about when I approach x equals 1 from the right?
1.
1.
Okay, I'm asking about the y value as I approach x equals 1 from the right.
2.
2, right? See the solid dot, right? F of 1 also equals 2. So what would you say about the limit as x approaches 1?
It is 2.
It
2.
is 2. Okay, and just for fun, I'm going to say f of 1 equals 2. So that's the nice, well-defined case. Everybody likes that. This is like what you have in polynomials, where your limit at any x value is the same as the function value. That's not always the case. Okay, let's take a look at B. All right, now I'm approaching x equals 2 from the left. What y value am I getting close to?
1.
And if I approach x equals 2 from the right, what y value am I getting close to?
1.
1.
1.
Okay, so since the left and right limits match, I can say the limit as x approaches 2 is 1.
1.
Okay, what's the function value at 2?
2.
Yeah, see the solid circle up here? Okay, so I can say f of 2 equals 2. Sorry, I gotta keep sliding my screen back and forth. All right, let's take a look at x equals 3. Okay, as I approach x equals 3 from the left, okay, what y value am I getting close to?
-1.
-1. So I can say the limit as x approaches 3 from the left-hand side of f of x equals -1. That's how I would write that. And how about as I approach x equals 3 from the right, what y value am I getting close to?
2.
Okay, so limit, oops, as x approaches 3 from the plus side, from the right, equals 2. I have two different values. Okay, so what can you say about the limit as x approaches 3? Can we make a choice here?
Yeah.
No,
Yeah.
you've got two different values, okay?
Oh, yeah.
If you get a different left limit from the right limit, you say the limit at 3 does not, as we approach 3, does not exist, right?
Yeah,
Because
that
they
makes
don't
sense.
match, okay? Now the function value at 3, that's the solid old dot at 1. Okay, so here's an example at 3, okay, where your left limit is one value, your right limit is another value. So the limit as a whole doesn't exist because you've got two different values. And the function value is yet a third value. Okay, see the three dots, two of them open, lining up. This is still a function, because if I draw a vertical line right here, the only thing I'm going to hit is this dot at 3, 1. Okay, there's nothing here and there's nothing here. Okay, take a look at that and ask questions if you're confused. No? Okay. Let's look at x equals 4. As I approach x equals 4 from the left, what y value am I getting close to?
1.
And as I approach it from the right, what am I getting close to?
1.
Okay, so I can say the limit exists as long as those two values match. Okay. Is there a function value at 4?
There is not.
Nope. So f of 4 does not exist. It's undefined. Okay, does not exist means undefined. Okay. Also, you'll notice I call this limit undefined because I can't choose. Okay, there's no rational reason to pick one of these limit values over the other. Okay, so the limit as a whole at 3 does not exist. Okay, because the function is not approaching one y value. Everybody good with this? Questions? The more examples you see, the better. Okay, kind of keeping an eye on the time. All right, I have one for you to try. Okay, you try example 5. Okay, I'll leave it up. Okay, type done when you finish. And again, you don't have to give me the function values, just the limits. Let's finish. Okay, so everybody give this a shot. Okay, I realize some of you are still working and that's fine, but let's just come together so we can make sure we understand this. Okay, so I'm going to speed this up a little. If you take a look at x equals 1, you can see that both sides of the graph are approaching y equals 1, right? So the limit as I approach x equals 1 is also 1. Okay, there's an open circle here and no dots, so the function value at 1 is undefined. Moving on to B, you can see as I approach x equals 2 from the left, I'm getting closer to y equals 1. And as I approach x equals 2 from the right, I'm getting closer to y equals 2. These are not the same value, okay? Graphically speaking, whenever you see a jump in a graph at a given x value, the limit will not exist there because you're going to have two different y values that you're approaching, okay? So this limit does not exist. Although the function value does exist, and that's 2. Okay, see the solid circle? All right, at x equals 3, you can see as I approach x equals 3 from the left, I'm getting closer to 2. As I approach x equals 3 from the right, I'm also getting closer to 2. So my limit is 2. Okay, the function value is a different value. Right at 3, the function value is a 1. All right, last one. Okay, as I approach x equals 4 from the left, I'm approaching y equals 0. As I approach x equals 4 from the right, I'm approaching y equals 0. So the function value, the limit value is 0. Also, since I have a solid dot right here at 4, 0, that's also the function value. F of 4 is 0. All right, so this is kind of a variety, a grab bag of all different types of limits. Okay. All right. Okay, so I'm guessing everybody's good with the graphical stuff. Okay, let's take a look at some algebraic stuff. Okay, I just want to make sure everybody remembers enough algebra to not get stuck. Okay, feel free to graph these things, okay, to give you some additional support. Okay, if I take a look and I graph this function, okay, I'll tell you right now, the numerator doesn't factor. Okay, I can tell that because there's only one way to get 3, okay, with everything being positive, and that's a 1 and a 3. That means my middle term would be 4x. Okay, so this doesn't factor. So this won't divide out. Okay, if I were to just plug in my 1 here, everything would be cool because, again, the problem, the vertical asymptote, isn't at 1, it's at 2. Okay, so plugging in a 1 into the denominator won't cause me any problems. Okay, and if you evaluate all this, you're going to get 1 plus 3 plus 3. You're going to get 7 up here over -1. So your limit as x approaches 1 will be -7. Okay, you ought to be able to see that on the graph too. There's no holes in this graph. Okay, so this is just going to be a smooth curve, and the y value when x is near 1 will be near -7. All right, so you'll be able to see that graphically. Okay, just a quick switch over to Desmos to prove what I'm saying. Let's see if I can do this quick. I'm going to repurpose my equation. Okay, so basically they wanted to know about the limit as x approaches 1. Well, again, the graph is probably way down here. Okay, I have to zoom out a bit so you can see it. Here's -1. And again, you can see as I get close, okay, both at -1, at 1, it's 1, -7. That's the function value there. And of course, since there's no hole there, that's also going to be the limit. Okay, so you can double check your answers graphically. Okay, let's take a look at this one. Okay, this one, again, I'm interested in what happens as x approaches 2. Well, you can see that would cause me a problem. I can't just plug in the 2 because then I'll wind up with a 0 in the denominator. Okay, so everybody remember from college algebra, if I have a factor in the denominator that's not shared by the numerator, remember I said this doesn't factor at all. What is x equals 2? Okay. There is what? What happens at x equals 2, folks? Anybody remember from Math 151? Okay, if a factor here in the denominator that's not shared in the numerator. Anybody remember what they give you? Vertical asymptotes. Okay, so there's a vertical asymptote there. It's the same graph. You can see the function's the same. So I'm going to take a look at my graph. I'm going to zoom out a bit so you can see the other arm. Okay, remember this is what you're used to for rational functions. And again, I don't know if you can tell. Let's see if I can graph. There's the vertical asymptote. Okay, I actually graphed it. And you can see the function graph is getting super close to it, but it will never equal it. Okay, and you can see as I approach x equals 2 from the left, okay, what happens to y? Okay, I'm typing this in the chat. As I approach x equals 2 from the left, what's happening to the y values?
They start to go to negative infinity.
Yep. Okay, they approach negative infinity. Okay. Oh yeah, and Desmos will use 2 lowercase o's for infinity, just so you know. And as I approach x equals 2 from the right, what's happening?
They go to positive infinity.
They go to positive infinity. Okay, everybody see that? So you've got like 2 problems here. Not only are the limits not the same, infinity isn't a number. Okay, so the limit as x approaches 2 does not exist. Okay, the limit as x approaches 2 does not exist. Why is that? Well, for the main reason is the function shoots off to negative infinity in one direction and positive infinity in the other. Okay, it's not getting close to any number. Okay, so you could determine this graphically. You could determine it by building a table. Okay, if I can use a graph, I prefer to use a graph. Everybody okay with that? Okay. Anybody questions? Questions so
No,
far?
it's making sense to me so
All
far.
right. I'm glad to hear it. I'm glad to hear it. How's everybody else doing? Everybody good with it?
We're good.
You're good. Okay, one thing I'm going to not take up class time with, but it will be in the notes, is I'm going to put more examples, okay, of using algebra to simplify finding a limit. Okay, why am I not going to show you now? Because it's kind of a review of Math 121 and Math 151. It involves things like rationalizing the denominator of a function. If you've got a square root, okay, how do you get rid of the square root? Well, multiply it by itself, okay? If only one term has a square root, multiply by its conjugate, right? Square root of x plus 2 in the denominator, multiply square root of x minus 2 to get rid of it. So you're going to have to reach back there for some of this algebra. Okay. And again, if you get stuck with the algebra, please ask. Okay. I'm more than happy to help you refresh your memory on that. It's just, I don't want to take up class time with it. Okay. So please look in the uploaded copy of the notes, and I will have at least 2 more examples showing you algebra weirdness. Okay. As far as evaluating a limit. Can you do them graphically? Yeah. Okay, you just got to be careful, and you got to look for those undefined spots in the graph. Okay, you have to have some sense of what the graph should look like. Okay, so I'm going to go back to my notes. And the last thing we're going to talk about is continuity. Okay, remember I said calculus is kind of, it works best whenever something is continuous. Okay, continuous means no holes, no jumps. Think of the informal definition. If you were trying to draw this on a piece of paper, you can draw it without lifting your pencil. That's a continuous function. Okay, so here's the mathy definition. Okay, the mathy definition is a function is continuous at a given x value if and only if the limit equals the function value. Right? We saw examples of this, right? We did a couple of examples and I said, okay, what's the function value? Oh, hey, guess what? It's not the same as the limit. Guess what? You've got a discontinuity there. But if the function and the limit at a given x value match, the function's continuous there. Okay? So here it is in English. A function is continuous at a given x value if the limit of the function as x approaches that value equals the function output at that value. Okay, so again, we ought to be able to eventually get to the point where you can look at a graph and you can pick out the discontinuities. Like, let's take a look at x equals 1. Okay, you're seeing, well, it looks like the limit is 2, right? Because there's a nice smooth connection here. Also, the function value is 2. So this function is continuous at x equals 1. Okay, because the limit as you approach x equals 1 equals the function value. Okay, how about at 2? What do you think? Is this function continuous at x equals 2?
Yes.
Well, you've got a limit for sure. The limit equals 2. But what's the function value?
1.
1. Okay. By the definition of continuity, it's not continuous. You've got a hole here. And even though the function's defined, it ain't defined where the hole is. Okay. Again, if you were drawing the function, you would need to pick up your pencil to get over the hole and to draw the dot down here. Okay, so this function is not continuous at x equals 2. How about at x equals 3? What do you think?
Doesn't exist.
Okay, the limit doesn't exist, right? Because the left-hand limit is 2. The right-hand limit is 1. So the limit right at as x approaches 3 does not exist. 2 different values. Okay, so that's enough of a problem. Okay, and the function value is one of those. Okay, so the limit has to exist in order for there to be a continuous function. Okay, so if the limit doesn't exist, well, your function value can't be the same as it. Okay, so take a look at the graph. Okay, this function has a hole at 2. That's a discontinuity. This function has a jump at 3. That's a discontinuity. Okay, here you also have a problem because although your limit exists and is equal to 2, okay, there's no function value at x equals 4. Okay, so again, your limit can't equal something that doesn't exist. So this is not continuous at x equals 4. There's a hole there. So hole, jump, hole. Those are discontinuities. Okay, and here's a table that shows all of these values. Okay, at 1, The function value at 1 is 2. The limit as x approaches 1 is 2. We're good. Continuous. Okay. At x equals 2, the function value is 1. The limit is 2. They're not the same, so not continuous. Okay. At x equals 3, the function value is 2. The limit doesn't exist. The function's not continuous. And at 4, okay, the function value is undefined. The limit is 2, not continuous. So the only place this function, of all the points they asked us to look at, the only one where the function is continuous as x approaches 1. Okay, so these are, again, the wording says it, but not continuous. And this is continuous. Okay, everybody good with that? I want you to develop an intuition about it, okay, especially when you look at it graphically. So if I'm going to do any calculus-y things, I'm probably going to avoid x equals 2, x equals 3, and x equals 4, because my calculus won't behave well. It will behave well at 1. And of course, on any of the points in between, okay, because there's lots of points in between these values. Okay, here's some more terminology, okay? At x equals 2, okay, and at x equals 4, we have holes in the graph, okay? We had limit values there, okay? Here the limit was 2, here the limit was 2, okay? As long as you've got a hole, that's called a removable discontinuity, since I could make the graph continuous by getting rid of the hole, okay? That's sort of like thinking of as like putting a patch on a tire, okay? That's a removable discontinuity. This jump here at x equals 3, that's a non-removable discontinuity. I can't do anything with that. There's no way for me to stitch the two halves of the function together. Okay, that's called a jump discontinuity or a non-removable discontinuity. Okay. A vertical asymptote is also a non-removable discontinuity because the function's shooting off to infinity and you can't do anything about it. You can't just patch a hole. Okay. All righty. Let's take one last look here. Okay, here's another function that's been through a lawnmower. Okay, and I'm asking you to find where the function, give me some x values. Where do you think the function is discontinuous? Okay, where are the discontinuities? Remember, you're looking for places where you have to lift your pencil to draw the function. Okay, so take a minute and look at it, and then be ready to share out. Okay, everybody get a chance to look at the graph? Let's take a look at -1. What do you think? Is the function continuous at -1?
Yeah.
Yeah, because the limit, the behavior near the value x equals 1 is equal to the function value. Okay. This is at 0, and I could certainly draw this without lifting my pencil. Okay. This is called a cusp, and we'll talk about what cusps give you when you do calculus, but it's continuous there. Okay, how about at 1? What do you think? Is this function continuous at x equals 1?
Maybe. No. There's a hole, right?
There's a hole, right? You'd have to lift your pencil to jump over the hole. Okay, the function value doesn't exist, so it can't equal a limit. It looks like a limit exists. They didn't give us a y-axis, so we can't tell what it is. but the limit here exists, the function value doesn't. So the first discontinuity is at x equals 1. Okay, this is 2. Okay, how about at x equals 2? Is it continuous there? Does the limit
It
equal
is
the
continuous at x
It's-
equals 2.
Yes, it is. Okay, because again, your limit is approaching the same value as the function value. Okay, how about at x equals 3?
Not
I
continuous.
have a function value, but what's going on here?
Vertical asymptote.
Right. Okay, so that isn't, I'm not approaching any given value from the left-hand side. Okay, so the limit doesn't exist here at x equals 3. Okay, I have a right-hand limit, whatever this is, but no left-hand limit. Okay, so the limit doesn't exist. So again, I'd have to say it's discontinuous at 3. And you can see I'd have to lift my pencil to get across the vertical asymptote and start drawing again. How about at 4? Is the function continuous at 4?
No.
No.
No. Why is that? Well, there's no limit, okay? Because my left-hand limit and my right-hand limit are different values. Even though the function value equals the left-hand limit, it doesn't matter. The limit doesn't exist here, okay? And you can see also, I'd have to pick up my pencil to draw my dot here and then the open circle here. All right, and the last one at 5, they didn't put a dot in. So I'll put a dot in and you can see, yes, the function is continuous at 5. Okay, everybody all right with that? So that's graphically. Very last topic, and then we're done for today. Okay, this is kind of interesting. It says these are both rational functions. Okay, and again, 3 conditions in the definition of continuity. What are those? Okay, f of x exists. The limit, or I should say, f of c exists. Limit as x approaches c of f of x exists. And f of c equals the limit as x approaches c. Okay, so these are the 3 conditions of continuity. Okay, you have to have a function value at the point you're considering. Okay, you have to have a limit at the point you're considering, and the function value and the limit need to be the same thing. Okay, that's what they mean by the 3 conditions. These are all rational functions, and they typically violate continuity in spades, okay, or at least in one point. Okay, here's a rational function. Anybody tell me what problem I'm going to have and where it's going to happen? Okay, again, the question's asking you, find at least one point where the function isn't continuous, one x value. Okay, so yes, okay, Richard's saying x equals 3. Okay, now you can tell from looking at that function rule, when you plug in x equals 3, you're going to get a 0 in the denominator. What happens at x equals 3? What do you got there? Okay, is it a whole? Remember, wholes are when the factors match in the numerator and the denominator. Okay, if it's not a whole, it's a vertical asymptote. Okay, vertical asymptote. Okay, so essentially what happens? Well, okay, the function value doesn't exist. Okay, so then f of 3 doesn't exist, right? Remember, at a vertical asymptote, you can't ever reach the x value. Also, the limit as x approaches 3 doesn't exist. Okay, so you can take your pick there. Okay, because the function is shooting off to infinity. All right, with this one, this is also a rational function. And again, we can factor this. Just so you know, guys, out there are websites and apps that will factor polynomials for you if they're factorable. Okay, if you need help finding those, let me know. Again, I don't want you getting bogged down in algebra. Okay, if there are tools out there, use them. Okay, so this function has a hole at x equals 2. Okay, so at a hole, the limit exists, right? And I can find the limit by plugging in a 2 over here in the part that's left. Okay, so this function would be approaching 5, 2 plus 3, when I get close to 2. But f of 2 does not exist. Okay, so it should be possible for you to look at a function rule like this and pick out points where the function has a discontinuity. Again, leverage the information you have from college algebra about rational functions, holes, and vertical asymptotes if they ask you to do something like this. Okay, so questions. Okay, the important takeaway from today is limits. Make sure you understand how to find a limit. Okay, I'm going to come back to our meeting and ask you again. Okay, anybody questions? Questions on anything?
No, not yet.